Hello, everybody, and welcome to another wonderful day of chemistry. So today we're going to be looking at alternative ways to pack atoms into a lattice. So last time what we did is we tried to pack all of our atoms into cubic lattices. So this is essentially putting them in more or less a cube. However, it turns out what you're trying to do then is put spheres into a cube. This doesn't always work that well because essentially we're trying to fit round objects into square holes. Not exactly the most intuitive way to go about it. So another way you can go ahead and look at this is doing what the favorite game of many children, which is how do you pack spheres? Round objects, what's the natural way to stack them? So the go-to starting place is you go ahead and pack all of the objects, again, in a constant layer, each slightly offset, getting them as close to each other as possible. From there, you then go ahead and put a single sphere in the middle of each of these triagonal holes. So that's pretty straightforward. However, from here, you've got two different options. You can either go ahead and put a sphere in this center hole, which is often called a tetrahedral hole because that hole will be adjacent to 1, 2, 3, 4 atoms, or you can go ahead and put it in what's called an octahedral hole, which is essentially slightly offset from where you originally started. So right here. The reason this is called octahedral is that center hole is now surrounded by 8 atoms. So 4 tetra, 8 octahedral. So these are our two options. What's very important, if you notice here on the bottom, is this gives us a very different pattern. So this first set of pattern has layers alternating A, B, A, B. However, in the second pattern, it goes A, B, C, A, B, C. So it repeats every 3 layers. And this gives a very different sort of structure. And really, it's this choice of the third layer that dominates our two close pack structures. So the simplest of which is this hexagonal close pack, where you're putting them in the tetrahedral holes. So again, each of these holes will be next to 4 separate atoms. So again, putting it right on top of the previous layer, or the original layer. When you do this, again, it's going to generate a hexagonal structure, as we'll see shortly. And common hexagonal close packed elements includes magnesium, titanium, zinc. So these are fairly common elements, and it can be extrapolated to any number of molecular and ionic species. So it's fairly nice and fairly tightly packed. The alternate option, going ahead and putting the atom in these octahedral holes, so here, here, here. So essentially wherever you see a white spot, this generates what's called a cubic close pack structure. So really what we're doing is we're taking the second layer, we're rotating it slightly to generate a third, and then repeating with the first. And you can kind of see it in this original layer. You set down a layer, you set down a second layer, you then rotate that layer 60 degrees, layer C, and then repeat. So again, a slightly different structure. However, it turns out if you go ahead and rotate the structure from a slightly different perspective, it turns out you can generate the face-centered cubic lattice. So it turns out that cubic close pack is just another name for face-centered, but it really helps illustrate that there's a lot of different ways to put together these crystal structures, but also the fact that the reason why the face-centered cubic lattice was so good is it is a version of a close packed lattice, even if it didn't originally look like it. So let's go ahead and take a little bit closer look at the hexagonal close packed lattice. So it has a repeating unit of a hexagonal cell, often can be thought of as a 3-dimensional hexagon. So again, a nice repeating unit, and you can then send it off up or in any of the given face directions. So it repeats itself fairly nice. However, this isn't exactly the best way to, well, replicate a cell in infinite directions. So oftentimes this is simplified as a 3-dimensional rhombus, which you can see here in green, where you have one atom at every given corner, and then one atom sitting here in the center. So again, gold is sitting in the center of this lattice, or in the middle of this lattice, and we have one atom at every angle. So this ends up being also able to be repeated in any given direction and is often used to depict the system. Now, then we have to ask our classic questions. So how many neighbors does each atom start with? And this one's a little bit trickier than some of the ones we've had previously. So I want you to go ahead and start by taking a look at this atom on the top and figure out how many neighbors it has in the same plane. And if you'll notice, it's connected to 6 separate atoms. So that's not too hard. That's really what helps form the hexagon. However, we also need to figure out how many atoms above and below. And you'll notice that if you filled this into a space filling model, it would touch each of these gold atoms below. So there would be 3 atoms below, and if you replicate it, 3 atoms above. So this gives a total of 12 neighbors, 6 in the plane, 3 above, and 3 below. So this is actually a fairly tightly packed lattice. This is more or less equivalent to the original face-centered cubic, which was so far the best lattice we had. And it turns out that if you look at the space filling model, it also ends up generating a 74% occupation volume. Yes, this is the exact same thing as face-centered. And let's go ahead and compare all of the lattices we've looked at so far. So far, it's pretty obvious. Simple cubic is a nice, simple model, but not that many elements tend to occupy it. But as we'll see later, it can be used for more complicated structures. Body-centered cubic, now we're starting to get good. Our coordination number has gone up, and so has our occupancy. It's almost as good as our 2 best close-packed lattices, hexagonal and face-centered, which you'll notice all 3 of these bottom lattices tend to have a lot of elements that give the same occupancy, and our coordination number goes from 8 to 12, being one of the reasons why some atoms prefer having a body-centered cubic. They can't generate enough electrons to make that many good neighbors. So this gives us a good way of looking at various ways we can pack a structure. However, next time we're going to go ahead and try and take these ideas and figure out how we might have to distort these lattices to generate ionic systems. Until then, take care.